Welcome to this lecture series in complex numbers. In this lecture, we'll be looking at a problem about regular polygons. We have looked at one such problem before, and this is quite similar, but still has interesting ideas. So here's the problem. Let a1 up to an be the vertices of a regular polygon. Here is a nice diagram showing it. Let r be the radius of the circle that circumscribes the polygon. So this pink circle, its radius is, let's say, r. Then the product of all these lengths. So you take a1, then this length, a1, a2, then a1, a3, then a1, a4, and if you product all these lengths, you get n times r to the n minus 1. So this is what we want to show. As usual, you're encouraged to pause the video and try to solve the problem yourself. And with that, now let us go to the solution. And before we go to the solution, we recall a fact about polynomials. So suppose we have a non-zero polynomial, then it has only finitely many roots. So if it were a constant non-zero polynomial, then it would have no roots. What are roots? Roots are the points where the function vanishes, the polynomial vanishes. So p in C is a root of f if f of p is 0. All right. So what we are saying is that if you have a non-zero polynomial, then it has only finitely many roots. In fact, what we showed was that if you have a polynomial of degree n, and n is some non-negative integer, sorry, n is a positive integer, then it has at most n roots. So that is what we saw, and that was a consequence of what is called the factor theorem or something. Basically, if z0 is a root of f, then you can find a polynomial g such that this happens, right? So that's basically why the number of roots of f is bounded by the degree of f. So anyway, this is a conclusion that holds, and a corollary of that conclusion is this: if we have two polynomials f and g which agree on an infinite set. So what do we mean agree? So we say f and g agree on a point p if f of p is g of p, meaning they take the same value at p. And what we have in the hypothesis is that suppose two polynomials agree on an infinite set, meaning there is an infinite set of points in the complex plane where f and g take the same value, then in fact the two polynomials are equal. And this is very simple, because just define a function as the difference of f and g. What this really means is that the value that h takes on z is the difference of the values that f and g take on number z. Right? And since f and g are polynomials, so is h. The difference of two polynomials is a polynomial. And by the hypothesis that f and g agree on an infinite set, we see that f minus g vanishes on an infinite set. And hence, this polynomial has infinitely many roots, meaning it vanishes on infinitely many points, and therefore this must be the zero polynomial. That's what this conclusion is. And therefore f equals g. So that's it. I'm not writing all the details, but I've said it. And now let us get back to our problem. So we have this diagram, and we may assume that so let's say these are the vertices of our polygon, and we may assume that the center of the circle, the pink circle, is the origin. And we may also assume that this number a1, so I will prove it for radius equals 1. You can get to the general thing by just scaling the the argument. So now we may also thus assume by rotating or whatever that a1 is 1. a1 is the complex number 1. Right? If you assume r is 1, then you may assume a1 is 1 just by rotating the entire polygon, and the center of the polygon is 0. So under those assumptions, what we want to really talk about is this quantity a1 up to an. But what is this? This is magnitude of 1 minus, so before I say that, let zeta be cos 2 pi by n plus iota sine 2 pi by n. So then what does a2 become? a2 is zeta. This is zeta square and so on. So a1, a2 is 1 minus zeta magnitude. a1, a3 is 1 minus zeta square magnitude. And a1, an is this. So this is the quantity which we want to show is equal to n times r to the n minus 1, but r is equal to 1, so we just want to show that this thing is equal to n. So that is our goal. All right. We put a boundary here. Oops. Okay. Yeah. But what is this? This is equal to 1 minus zeta square dot 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 1 minus zeta to the power n minus 1. All right. And now let us freeze it here for the moment. What we know is on the side, we know that. So let me use a different color. Now we have this expression is equal to z minus 1, z minus zeta, dot 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 z minus zeta to the power n minus 1. Right? Because these are precisely all the n roots of unity. And by the factor theorem, or however we want to see it, we have this is equal to that. Right? And now this implies that this is equal to z minus zeta square dot 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 z minus zeta to the n minus 1 for all z not equal to 1, because we are dividing by something, and if you're dividing by something, that something shouldn't be 0. So for z not equals to 1, we have this equality, which implies 1 plus z square plus dot 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 z to the n minus 1 is equal to the right hand side. For z not equals to 1. So all we did was that this is equal to that by the geometric formula. Right? So the left hand side is a polynomial, the right hand side is a polynomial, and they agree on an infinite set. This set is infinite, right? All complex numbers other than 1 form an infinite set. So this should be equal everywhere, not just outside, not just in this infinite set, but they should be equal everywhere. That is what we concluded earlier. So in fact, we get that this is true for all complex number set. And now we can substitute z equals 1. So this implies, so now the color is back. So this implies 1 plus 1 plus 1 plus dot 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 plus 1 equals 1 minus zeta squared dot 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 1 minus zeta to the power n minus 1, which implies n is equal to this thing. And you can take the magnitude on both sides if you like, but that doesn't change anything. It's already a real number, already a positive real number. All right, so this shows that this quantity is n, and the general, if the radius were not assumed to be 1, you would, when you would do this, n r to the n minus 1 would pop out in the beginning. So it's the same thing. And so that's a very nice solution to a fairly complicated looking geometric problem. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.